Numeric abstract base classes. Source code numbers.py. The numbers module PEP3141 defines a hierarchy of numeric abstract base classes which progressively define more operations. None of the types defined in this module are intended to be instantiated. Class numbers.number. The root of the numeric hierarchy. If you just want to check if an argument x is a number without caring what kind, use is instance x number. The numeric tower. Class numbers.complex. Subclasses of this type describes complex numbers and include the operations that work on the built-in complex type. These are conversions to complex and bool, real, image, plus, minus, multiplication, forward slash, double power, abs, conjugate, equal, and not equal. All except minus and not equal are abstract. Real. Abstract retrieves the real component of this number. Image. Abstract retrieves the imaginary component of this number. Abstract method conjugate. Abstract returns the complex conjugate. For example, 1 plus 3j dot conjugate equal 1 minus 3j. Class numbers dot real. To complex real adds the operations that work on real numbers. In short, those are a conversion to float, math.trunc, round, math.floor, math.ceil, div mod, slash, percentage, less than, equal to, greater than, and greater than equal. Real also provides defaults for complex, real, imaginary, and conjugate. Class numbers.rational subtypes real and adds numerator and denominator properties. It also provides a default for float. The numerator and denominator values should be instances of integral and should be in lowest terms with denominator positive. Numerator abstract, denominator abstract. Class numbers.integral subtypes rational and adds a conversion to integer. Provides defaults for float, numerator, and denominator. Adds abstract methods for power with modulus and bit string operators. Operations left shift, right shift, exclude, bitwise and bitwise, XOR, bitwise or and inverse. Notes for type implementers. Implementers should be careful to make equal numbers equal and hash them to the same values. This may be subtle if there are two different extensions of the real numbers. For example, fractions.fraction implements hash as follows: def have self.denominator is equal to 1, get integers right, return hash self.numerator. Expensive check but definitely correct. If self is equal to float self, return hash float self. Else use tuples hash to avoid a high collision rate on simple fractions. Return hash self.numerator and comma self.denominator. Adding more numeric ABCs. There are of course more possible ABCs for numbers, and this would be a poor hierarchy if it is precluded the possibility of adding those. You can add myFoo between complex and real with class myFoo complex. myFoo.register real. Implementing the arithmetic operations. We want to implement the arithmetic operations so that mixed mode operations either call an implementation whose author knew about the types of both arguments or convert both to the nearest built-in type and do the operation there. For subtypes of integral, this means that add and radd should be defined as class myIntegral integral def add self other. If is instance other myIntegral return do my adding stuff self other. Else if is instance other type no I know about, return do my other adding stuff self other. Else return not implemented. Def radd self other. If is instance other myIntegral return do my adding stuff other self. Else if is instance other type I know about, return do my other adding stuff x other self. else if is instance other integral return integer other plus integer self, else if is instance other real return floating float other and float self, else if is instance other complex return complex other plus complex self, else return not implemented. There are 5 different cases for a mixed type operation on subclasses of complex. I will refer to all of the above code that does not refer to my integral, another type I know about as boilerplate. A will be an instance of A which is a subtype of complex A less than complex and B colon B less than colon complex. I will consider A plus B. If A defines an add which accepts B, all is well. If A falls back to the boilerplate code and it were to return a value from add, we would miss the possibility that B defines a more intelligent add method. So the boilerplate should return not implemented from add method, or A may not implement add method at all. The B's add gets a chance if it accepts A, all is well. If it falls back to the boilerplate, there are no more possible methods to try. So this is where the default implementation should live. If B less than comma colon A, Python tries B dot add before A dot add. This is okay because it was implemented with knowledge of B, so it can handle those instances before delegating to complex. If A less than colon complex and B less than colon real without sharing any other knowledge, then the appropriate shared operation is the one involving the built-in complex and both R's land here. So A plus B is equal to B plus A. Because most of the operations on any given type will be very similar, it can be useful to define a helper function which generates the forward and reverse instances of any given operator. For example, fractions uses diff operator, fallback monomorphic operator, fallback operator, diff forward AB. If is instance B integer fraction, return monomorphic operator AB, else if is instance B float, return fallback operator float A B, else if is instance B complex, return fallback operator complex A B, else return not implemented. Forward dot name is equal to underscore fallback operator dot underscore name plus underscore underscore. Forward dot doc is equal to monomorphic operator dot doc. Diff reverse BA, if is instance A rational includes integers, return monomorphic operator AB, else if is instance A real, return fallback operator float A float B, else if is instance A complex, return fallback operator complex A complex B, else return not implemented. Reverse dot name is equal to R plus fallback operator plus name plus underscore. Reverse dot underscore underscore doc equal to monomorphic operator dot doc. Return forward reverse. Diff add AB A plus B, return fraction A dot numerator multiply B dot denominator plus B dot numerator into A dot denominator comma A dot denominator into B dot denominator. Add comma R add is equal to operator falls back fallbacks add operator plus add. Thank you.